All right, welcome back to part 8 of Design a Computer from Scratch. In this video, we will take a look at the opcode decoder and, even more importantly, the core of the whole design, the timing design. We're going to take the game up here a little bit and do something that's we've delayed putting off, delayed and put off, but we're going to bite the bullet and you'll get to see what it is. So just as a refresher, what does the opcode decoder and control timing section here have to do? Well, it needs to control the program counter. It needs to increment the program counter. It needs to load the program counter. It needs to control the load of the register file, that strobe. And it needs to deal with the ALU Z-bit. Well, the ALU itself will generate that Z-bit, so we're not quite there yet. That'll be the next video. We've decided early on that we needed multiple clocks. There's a few reasons for that. One is you hit the program counter and it increments on the next clock, and there's a output delay, not prop delay technically, but an output delay from clock to the next data value or the next instruction value out of the ROM, so we need some clocking for that. We also want to make some strobes for I/O, so we want a 2-clock strobe for reads and 1-clock strobe for writes. So we need some time, and decided on here for the sake of efficiency that we would come up with 4 clocks for the instruction, and have decided not to use just a regular counter. There's good reasons, we'll talk about that, mostly due to making glitches, but using what's called a gray code counter. That doesn't count 0, 0, 0, 0, 0, 1, 0, 1, 0. It counts by changing only one bit at a time between states. So it'll go from 0, 0 to 0, 1 to 1, 0, 1, 1 to 1, 0. Kind of a weird count if you're looking at it in terms of decimal, going from 0 to 1 to 3 to 2. But if you look at it a bit-wise and look at pairs, this only changed the bottom bit, this changed the next bit, this one changes the bottom bit, and then this back to here, because it'll loop around forever, just changes that bit. So there's a big value in having that. If you generate something that's a couple of clocks wide, you don't get the potential glitch between the counts. Well, I decided to jump the gun earlier and already did the decoder. So we already have our 7 instructions signals for them in the CPU underscore 001.vhd file. That's those 7 signals that are the op for the opcode, and load register immediate down through jump. And we've already again dealt with those decodes here and generate all of the individual strobes for those individual instructions. Now, they're not gated with a clock or anything in here. It's just purely, hey, if the ROM data's got this value on it, then set that bit. So other things that use them will have to deal with them and generate strobes, but they should bound anything that needs to be done with the 4 clocks that we have. So like I said, we're going to use the gray code counter for glitch-free decoding. And let's create the entity for that first. The entity, we'll give it its own file name, graycode.vhd. Try to stay obvious here for what it does. Same thing for the entity name. Remember, this appears 3 times, that gray code 3 times. The inputs are a clock, reset. Well, we're not using it currently, so we're going to set it high. But if we want to reset this back by maybe pressing our button on the card to reset the CPU or something like that, then we have that ability. So we built it in here, but it's not doing anything in the current pull-up condition here. It's just as if you put a 10K pull-up resistor on that pin if it was a chip with a pin. And the only thing that comes out is those 2 gray code bits. So let's take a look at the implementation of it. It's a pretty simple implementation, including the reset. If reset is low, we're using N for active low here, then the gray code goes to 0. Otherwise, if the gray code is 0, 0, go to 0, 1. If it's 0, 1, go to 1, 1. If it's 1, 1, go to 1, 0. And back to 0 again at the end. So we don't need that extra when, because it's the only things that are left. We had to add a gray code signal inside of our gray code VHDL file with those 2 bits, standard logic vector. And we're creating, this is a little bit interesting the way this works. We're creating this element outside of a process loop. It could be created in a process loop, but we're just creating, this is that preload value, and then we're latching that value out. There is an error here that we'll catch, and the error is that this should have used the output gray code bits, and that also would imply, if we're using that, that this entity pin needs to be an in-out, not just an out. So adding it into the top, we have to add a signal for those gray code bits because they're used all the way through the CPU_001 VHDL file. And this reserves those 2 wires for that for the gray code. And the entity hooks up like this. Right now we're even going to force it here to a 1. We could have just left the line off because we already pulled it up inside of the gray code file. And remember your colon and work dot and adding the word map and not including the line after it when you copy paste it. But iClock just hooks up to the 50 megahertz CPU clock. Like I said, resets pulled up to 1. And the output of the gray code from that gray code part gets hooked up to these gray code wires. So let's think about a little bit about flow control right now. If it's a jump, it will always load the PC. If it's not jump, then at the moment, because we don't have branching, branch on 0 equal to 0 and branch not equal to 0, at the moment it will only do jumps. So we only have to implement that. We'll do more as we go along here, but let's start there. And remember when we designed the program counter that if you hit the load, it has priority over the increment. So we can pretty safely always increment the PC or hit the increment line. And if we happen to be doing a jump instruction here, then at that gray code value of 10, which if you remember was the last 00, 01, 11, 10. 10 was the last state. That's where we'll tell it to increment. So when the gray code has 00 on it, it has a new address presented at the beginning of the 00, and after that 00 state, it will have it propagated through the ROM. So anything we do will be out in the 01, 11, or 10 gray code values. That's where we'll play around with it. We do want to remove the default values that we had set for those. They had equals something out here. I think we'd set them to 1 or something else, but basically now we're driving them. So it's single clock wide. It's combinatorial here. Could be set up to be less combinatorial. It could be set up to be registered if we wanted a little more timing flexibility. Move this back 1 clock. The jump's there in plenty of time. It comes out as soon as the ROM data's true. But combinatorial will work just fine for this. It's not that complex of a piece of logic. So all of our increments and loads will be done at state 10. Otherwise, pardon me, otherwise it'll just increment. And like I said, we removed the default values. So let's wire up the register file contents because now we have enough bits to do things useful. We want to load the register file for 2 types of instructions in what we currently have. Load register immediate, and we'll load that at that state 10 again. And an IO read, same thing. It'll read it at 10 here as well. We'll perform the read only on 1 clock wide, although the strobe to the peripheral bus, the read peripheral strobe, is 2 clocks wide. We'll only latch the data in on the 2nd clock. So that'll make a load register file signal, and normally it's not going unless it's one of these 2 instructions and at that particular gray code. So that means we have to remove the default signals now that we're driving that register file, the load, and we're no longer going to be having it 1. We're going to get rid of that. Now we're at the point where we can hook up the register file select to select the correct. Could have done this earlier when we had the program counter, but it's or the program, yeah, the ROM created, because the ROM is where those register selects come from, bits 11 down to 8 of the actual instruction being done. But let's hook that up here, and everything else is done. We've created that load. We already had the register files in and out. We already made the muxes for where they go in the demuxes. At the moment, we're going to continue to fake out the ALU. This is the case. I noticed I didn't make the W underscore not following NANLAN's convention here. Wish I had, because that's just the right thing to do in my book. But we do know this is an ALU signal. Let's change it, because right now that we have the register file working, we can, instead of hard loading that out, we can actually loop back the register file as if it was a data out. Now when we make the ALU, this data out's going to come out of the ALU, not out of the register file. But right now, if you did a AND instruction of D0 with something, it'll just write it back in. We don't have the ALU to actually do the ANDing operation. That'll be the next slide. Mentioned previously, 1 clock wide at state 3 for IO writes, and a 2 clock wide at states 3 and 2 for IO reads. Writes can happen earlier. They don't have to wait till later. Reads, making it 2 clocks wide, is helpful. And this is where that glitch usefulness of the gray code can be seen in this read strobe, because instead of looking at 2 bits and saying this 3 or 2, we can just say if this most significant bit is set. And the fact that that bit only changes, the bits below it can change, but this bit doesn't change, produces a nice, very clean, glitch-free output. If you ever have stuff that you run and it gets real flaky and you can't really figure out why, sometimes it's due to this decoding. If we're decoding a counter and you want to say, hey, is this counter that? Unless the output of the comparer is registered up in some way, you will get glitches and things can go bad. So this is just something you learn if you've been playing with this stuff for a while, but it's worth reading up on gray codes, and I'm sure there's better introductions to why they're useful for making glitch-free designs, but this is what you want to do. All right, so far we've just played with switch and a light, but things are getting more complicated, and I think at this point it would be useful to hook up the peripheral bus signals to a tool called Signal Tap. And this video is going to be a little bit longer because of introducing signal taps, but imagine you have a very expensive logic analyzer sitting on your bench next to you, next to this card, and you wired everything up, and you want to see what the values of those signals is. Well, this SynKeep attribute and the use of that attribute, if you follow this sort of pattern, it will make these pins available to the signal tap peripheral inside of Quartus. You have to recompile after you do this, because it doesn't know those until you recompile the part. Well, not sure what happened to that slide. Block diagram of the RTL netlist. I just took a quick snapshot of what the block diagram looks like at the moment. It's really hard to read, but our gray code counter drives everything from back here. Here's the program counter. Here's the ROM itself. There's various other multiplexers and pieces inside of here. You can see some of the stages of multiplexers into the register file and the control lines that control that. So sort of a good visual representation. It's not a horribly complicated device. The parts that are their own VHDL file, if you double click on that part, you could go in and see what that individual part looks like, but this is a good representation of the block diagram. At this point, we can calculate the CPU performance. As a little side note here, we earlier estimated it, but I think we're there to know now. The CPU, or the FPGA, runs at 50 megahertz, and we have 4 clocks per instruction, which divides out to 12.5 MIPS. It's a pretty good performance for a small CPU, definitely better than a 1970s generation 6800 or 6502 or Z80 type of processor. Those might have run at 4 megahertz, and they would take multiple clocks per instruction. Now we have a lot less complicated instructions. They're all within one 4 clock beat. And again, also this is much faster than a TTL computer. I think Ben's maybe runs at a megahertz sort of a speed, but the ROM easily can run at the 20 nanoseconds clock to output data, timing, and everything in here should timing close at 50 megahertz. Let's do some testing, and we're going to now use the Signal Tap Logic Analyzer tool to do that testing. In Signal Tap, you get into it by clicking Tools, and then Signal Tap Logic Analyzer. And if you come in here, you should see USB Blaster detected. If not, I've had some fiddliness with this, just like the downloads, and sometimes you have to go and play around with stuff. Sometimes I've had to disconnect other USB devices and things, but generally it just comes up and works. If it doesn't, click the pull down and look and see in the next screen if you can find it. If not, might in the end have to find a help forum. But this normally works just on occasion. Sometimes the very first time you set it up, it's a little bit fiddly. First thing you want to do here is do that, and then after that it'll go out and find the device, which doesn't seem to ever have anything to do with the actual part that I'm doing. Hard to tell though, it could be over here in the letters off the screen. And the next thing you want to do is to associate it to the download file that you're using. Hit the triple dots there, browse to the folder that your SOF file is in, your download file, and in my case it shows up in the output files folder off the design a CPU folder, so that's where I'd find it. Double click it and that'll select that as the file that you're using for this design. Now at this point, the first thing you want to do is to click this little button over here next to the clock, and we want to use our CPU clock, that 50 megahertz clock, to clock this machine, this logic analyzer. It's just like a normal logic analyzer with state, where the state is driven by whatever you drive into the clock input to the logic analyzer. But after you click that button, the node finder will pop up. In our case, we're looking for I_clock, which is on pin T2. It'll also look at individual internal things, but T2 iClock is what you want to select. You can either right arrow it and have it go over, or you can double click it and it'll pop over here. And then you want to click, didn't put it there, but you want to click the OK button. If this is clocks, it has OK. If it's nodes, you're going to put in the node list, that'll have insert. So to add nodes, well, we've only got a clock into our logic analyzer at the moment, but we want to monitor nodes. So you double click here where it says double click to add nodes in very light gray. And when you get in there, you hit the list button again, and you can see the things that are already detectable. I like to set this to Signal Tap Presynthesis because it might give me more things than the list down here. But let's go ahead and select the gray code because I want to see what the gray code's doing. And either double click it or click the arrow. You can also expand it and do the individual gray code bits, but you can do that on the previous screen anyway when you go to view it. When you're done picking all the nodes you want, click insert, it'll shove it in to the screen as you see here. The two things you have to play with when you get to this screen are the trigger enable. Right now it's going to trigger on something, and in this case it's going to trigger on XX in the gray code, but if you want to shut that off, you just click it and then it'll run free. The way you run it we'll show in a minute, but it's to click this button up here. But before you do any of that, you still have to recompile it. Here's some other nodes I think we can look at without doing any serious work. Probably the most interesting one is the program counter. Again, we're going to shut off the trigger for all of these. Load program counter, increment program counter. We never really checked to see that they worked when we designed the program counter or anything. And this is a good opportunity to see if it clicks on state 2 like it should. And just for fun, let's look at the ROM instruction, the 16 bits of instruction out of the ROM, and see where that shows up. So you have to recompile. Like I said, you can do that from here inside a Signal Tap if you click this little blue arrow up here. It usually gives you a warning that I find hard to read, which is start rapid recompile. When you're done compiling, it'll do the little thing down here, 90%, 100%, and you'll know when you're done. You can click this button here to download now that file that you just created. Don't forget to recompile though, because The changes you made to Signal Tap will not show up in your design until you recompile and then re-download. While we're here, we might as well save that. I'm going to save it as CPU 002 part 8.stp Signal Tap file. And I'm going to do yes to enable it for the project because I want to turn this on for the design we're building. You can turn it off and on in the settings inside of Quartus, but for now we'll just turn it on. To go ahead and run it, you click this little blue arrow up here, and that will start the machine, the state machine running. You've already downloaded the file, and it's already running on the FPGA, but this starts the capture, as if you press the capture button on your logic analyzer, and it'll capture all of these items. So what do we get when we see that? Something's wrong, I think. We get that the program counter is 0 and the ROM data is E000. Well, that's correct. That's the data we have for the program we're running. But looking at the gray code, I don't see it changing, and expanding the bits just shows they're both stuck high. So there's an error in the code for the gray code, and you might have spotted it earlier. I think I mentioned it. I'm going to do something for that error. We had these set to W gray code, so what was happening is, because this isn't a clocked entity, those bits would just rip all the way up to 1 and they would stick there. So let's change that to the output, which is the latch version of them. Then this will only change and set the preload for the gray code at one time. Once we use something down inside of here that was an output pin, we have to change it to an in-out to tap it back into the FPGA. So that'll fix the gray code counter. When we run it, we can now see it working. So it's going from state 0 to 1 to 3 to 2 to 0 to 1 to 2 to 3. And it's just keep to 3 to 2 to 0 all the way. It just keeps looping, looping, looping forever, just like it should. We can see the program counter. Well, we have a jump to 0, I think, is our instruction we're running, so it's not going to have anything in it. But we can see two things. We can see our load PC and our increment PC. Remember, load has priority over increment, so it'll reload. And what's it loading? It's loading 0. And we can sort of prove that right here because the instruction is an E000, which is a jump, and the address is going to jump to is 0. So we're not going to see any activity here on the program counter, but we do see the ROM reading. We see these strobes. They could still be wrong, but at least the jump is working. We know for sure that it's reloading that address and not incrementing. Mentioned earlier that if you pick an unimplemented opcode like 00, it has no action on the registers or I/O or ALU. It's coded currently in the no-op as an assembler, and it could be turned into a pseudo-op if you want to reclaim the 00 opcode, but currently it's hard-coded as 00. And let's play with the code. So let's throw in a no-op in that code and look at what the listing file would be. It's the start here, address 0, address 1 has a jump back to start, so no-op, jump to start, no-op, jump to start. Kind of do that forever. Go ahead and load that, and you have to update the memory initialization file. Sometimes you want to click a couple of buttons to do that inside of I believe it's the tools button, or the button to the left of that. It says update memory initialization file. Sometimes you can just hit compile and it works. Haven't quite figured out what the pattern is there, but I usually do both. And it'll pop up a little message. Now the thing we have to do to load that new ROM, we're set to another ROM file, so we want to go into hierarchy, double click on that ROM, and it'll pull up the wizard here and do a couple of steps to get over to the MIF file. Remember, when you get here, if you see nothing, in this case it's in design a CPU /CPU code, but if you see nothing, go down to that selector down there for the file type and make sure you select the MIF type, and then these will pop up. And at this point we can exit out or finish out of the ROM file. We've updated the ROM file, and we might have to do a update memory initialization. Well, after we did that, we can see that the address is counting, and it is alternating between address 0 and 1 just like it should. We can see that right here on the program counter. For 4 clocks it's 0, and then for 4 clocks it's 1. The other thing we can do here is note that although the program counter started here at 0, the data isn't available till a clock later. Mentioned this a few times. The ROM file is registered of the address going in, so it won't see that new address until this clock later. Now again, this is a state machine timing logic analyzer, let's say, and so of course it doesn't have detail time. You don't know the exact how many nanoseconds this is, but it's capturing on the clock what the values of all of these registers are on that 50 megahertz CPU clock. So you now own many channels, pretty deep logic analyzer that you build into your design, and then you unbuild it by just shutting it off when you're done debugging. The ROM, we can also see while we're here the load PC and increment PC. Again, load having priority, but we can just see an increment here. So we'll go from address 0 to address 1 when increment's there. When load's there, it loads it back to 0. That was that jump back to start that we saw in our code. And we can see the two different opcode values, the no op, which is coded at 0, and the jump, which is coded at E1000. So it looks like everything is working in this setup here. Didn't have to do much debugging. The only thing that was broken was the gray codes, and that was just forgetting to put the registered values on the decode for the next state of the device. Now that we're here, let's go play with our peripheral unit and see what's going on. Those I/O reads and writes, address, data in and out, we ought to be able to do. So let's do a little test program here and have our test program write out our load register 0 with the value of 55, and then do an I/O write of that register to address AA. So I'll have two different addresses. Now there's nothing in the peripheral design that indicates that there's no devices out there, so this isn't really doing anything, but we ought to be able to look at the strobes and everything. The list file it generates has exactly what you'd expect mapped from up there. So Quartus will unfortunately optimize away the bus because there is no peripheral to write to. So let's solve that problem. And so we really can't look at the signals, but let's solve that problem by creating a simple I/O register. Make a register that when you write to it at address AA, it writes into a register, and when you read address 55, it reads back the complement of that data. So we can look concretely and see that not only are we writing something, but it's coming back as the complement, the logical complement of what we wrote. So the code we'll write for that peripheral test, we're going to put it in its own VHDL file. This is where all the peripherals ultimately could go, or we could make a higher level that calls the CPU and then put the peripherals off there. But for now, let's just go down this path of making Alexa stop. Let's make a module called or VHDL file called perif test reg. Simple register to test. Very similar pattern to what we've done before. NAND naming convention. It's going to be a clock device. It's going to have a single write strobe. Doesn't need a read strobe. That's done by the input multiplexer. It needs data in and it needs data out. So it's peripheral register data in and peripheral register out. That's all we need for the entity. We're going to save those 8 bits on 8 wires with a signal. And basically it's pretty simple. If there's a clock, if I clock's going, that 50 megahertz clock, and if the write strobe is there, then take what you wrote in, complement it with the not, and write it out. That's all there is to our little test peripheral here. That could be an LED, it could be anything. So let's add that into the top, the CPU underscore 001.vhd file. We need a peripheral test register write and a peripheral test register read. Well, we really probably don't need the read, but we sort of do. It could just read for any peripheral, but let's pretend like we care about that. And the instance of the device here is just the entity that we created with hooked up to these signals. So the peripheral write is the only thing we need here. Doesn't need a read. And then peripheral data in is data from the CPU. So this is kind of a useful convention. What goes out of the CPU goes into the peripheral. What goes out of the peripheral goes into the CPU. We'll make that write strobe go, the write select go high when the peripheral address is 55. We'll make that read go when the peripheral address is AA. Adding something down in here into the register file input data mux. we'll add if it's a read instruction and that peripheral read is here, then take that peripheral data to the CPU and move it into the register file, and the rest here will stay the same. So let's capture what that does. Wrote a little program that does that, and we can see it operating here. Quite a few more things on the waveform here. We can see the instruction running, the 605570AA. Notice the H is for hex at the end of it, the E000, and then the looping. We can see the address it's running through here. On the program counter, it's at 012, so it's a larger program. We're seeing more of the program counter work, enough to convince us it works. We still see the load and the increment work like it should, and we're actually seeing the peripheral write strobes going here. And if we look at the data in and the data out from the peripheral, we can see it doing what we would expect it to do as well. So it's working. We're writing something, we're reading it back as the complement. So what did we do? Well, it wasn't too bad. We created a gray code counter for the control of the timing. We verified that the program counter is working, and probably the coolest is we introduced signal tap to do debugging, and with a fairly simple example here, and got it working, and we're able to see stuck bits and fix those on the gray code counter, and verified the operation of other things that we'd sort of been putting off because we didn't have a good way to verify them without making a more complicated test. I/O reads and writes worked with a simple peripheral. We're able to write to something, have that something complemented, and then read it back and see it coming back complemented. And we also know that the load register immediate register file writes and reads are working. That's something we'd perhaps not verified as we should have. The two things we haven't done yet that were in the original design goals are we don't have an ALU yet. That should be a pretty simple block. And we don't have any conditional branching on instructions like branch of equal to 0 and branch not 0. We do have jumps working, so we know we have the basic methodology done, but we need to add both of those in. And none of this is complicated that's left, but it's definitely useful to have an ALU. You really can't do a whole lot with that except move stuff from here to there. With an ALU, you can start to test statuses and look at bits and things of that sort. And with branching, you can then loop on waiting for status of something, which you typically do with peripherals. As usual in the last few videos, we've made a repo for this, misnumbered, but this is what it's called up in the GitHub repo. It's CPU 001 part 8. It's in a branch. You can select it inside of GitHub. If you don't know how to pick branches, it's not too tough. You can probably figure it out, but there's probably help videos on that out there. The current build is up here. As of the time of this video, it has all of the things in the basic processor design done. It's got the conditional branching. It's got the ALU implemented. But if you're following along and want to play with the branch, this is the branch that matches where we're at the moment. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.